Hi everyone. Welcome to AP Physics C E&M, Electricity and Magnetism. This is the first video of the course that I want to go through, and here we're going to get into an introduction to electric charge, electricity in general, and eventually electric forces. So first, some citations. When I say chapter 25 at the beginning of this, we're talking about chapter 25 of the now classic book by Randall Knight, this being the third edition of that book. And the Randall Knight book is a really great physics book because it gives some very good, unique types of explanations for a lot of concepts. In many situations, these explanations are better than anything that I found in any other books of a similar level. I would say that it's also a very good bridge between somebody who has either not much knowledge about physics at all, or just maybe they had a non-AP or non-calculus based physics course in the past, compared with a lot of the textbooks that are used at a lot of high schools and universities for intro calculus-based physics courses. This is kind of a good bridge between people with no knowledge and some of those slightly more difficult books. For example, the Halliday-Resnick-Walker books, and the famous Tipler book, which is also a really good book, but maybe at a slightly higher level, but still for the same level of class. And also, throughout these slides and these presentations, I'll use certain resources or other items created by Tony Wayne, who was my mentor at my previous school. He's an awesome teacher and an awesome person at Albemarle High School. And also I'll occasionally use stuff from the Desmos online calculator. So without further ado, sometimes I'll cite some images that I use here as well. Some motivating questions. Are you really safe inside of a car during a lightning strike? How many types of charge are there, and how do we know that? And why can you pick up small pieces of paper with a comb after you have combed your hair? And how does the LCD screen on a projector turn pixels on and off? Just some motivating questions that you might be wondering about as you get into a course on electricity and magnetism, or you might be wondering about them now that I have posted them. So how does charge work? Well, electricity is a part of our everyday lives. It literally means the flow of electrons, and sometimes we'll take this literally, other times we'll just kind of use this as something of a model, and what we'll really think of is thinking about the flow of positive charge in the opposite direction. So some eerie results first of all. So if you vigorously brush or comb your hair, the brush or comb will be able to pick up little bits of paper and other small objects, but a metal comb will not do this. And also, vigorously rubbing silk to two plastic rods and a glass rod will result in the following. If you hang one of the plastic rods, and when the other plastic rod is brought near, the rods will repel. At least the ends of them will repel, or at least wherever you rub them. But when the glass rod is brought near, the two rods attract. And if you rub these things more strongly, you'll get a stronger reaction. And if you increase the distance between the rods, you're going to get a weaker interaction. The second of those kind of goes without saying. If that was not the case, then you could imagine getting an infinite amount of energy with infinite distance separation, which we're not going to have here. And when the plastic rod is hung before any rods are rubbed, there are no effects. In other words, if you don't rub a rod, then you're not going to have anything going on. So, is this eerie? Ooh. Some more eerie results is that a plastic rod that has been rubbed will pick up little bits of paper, just like the comb did. I mean, after all, we were talking about like a plastic comb. And a glass rod will do the same thing. However, I will also mention that there are no objects that can pick up bits of paper and attract both plastic and glass rods that have been rubbed. What this tells us is that there is some interesting phenomenon in nature that causes these interactions. We call it charge, and that there are exactly two types of charge. or at least I should say, we call this electric charge. So there are two types of electric charge. We give them names. We call them positive and negative. That works really well because they have certain mathematical aspects that work also very well when we consider them as literally mathematically positive and negative. So this is quite unlike the strong nuclear force in nature, the strong force, where you're dealing with three types of charge that we call color charge, that is very much not directly related to this electric charge that we're talking about here. So electric charge, there are only two types of charge. There are precisely two types of charge, and that's it. So some conclusions are that these frictional forces of rubbing add or remove this charge, and with these two charges, well, two like charges, in other words, two plastic rods, two plastic charges, will repel each other, whereas two opposite charges, like glass charge and plastic charge, will attract each other. And this is a long-range force that increases the more you do it, but decreases as you separate the distance between the objects. Neutral objects, in other words, the plastic rod that had not been rubbed yet, have an equal mixture of these two types of charge. And when you rub them, somehow you're able to rub off some of that charge. So continuing the experiment shows that touching a rubbed plastic rod to a metal sphere allows the sphere itself to pick up bits of paper, unless you have rubbed your finger along the rod. And connecting a metal sphere to another with a plastic rod will not allow the second sphere to do this. But connecting a metal rod to another metal sphere does allow the other sphere to pick up bits of paper when the first sphere is touched to a plastic rod, as well as repel a rubbed glass rod. So apparently charge can be shared in certain types of situations. So it can be transferred by contact, but there are two different types of materials. We have things that we call conductors, and we have things that we call insulators. With conductors, charge is free to roam around. With insulators, the charges are stuck in a particular spot. We now recognize that they're stuck to their particular parent atoms and molecules in the case of insulators. Benjamin Franklin established the convention that a glass rod that has been rubbed with silk is positively charged. And should note that while there are electric forces that act at a distance, objects cannot actually become charged without there being some sort of contact. So, for example, being electrically neutral definitely does not necessarily mean that there is no charge. In other words, charge can be rubbed off and transferred by contact to some other items that are uncharged or that are charged, and that could either add to their charge or help to cancel out the charge if the charges were originally opposite. Now, if you've had a chemistry class before, you know about atoms and how the nucleus of the atom is positively charged and contains protons and neutrons, and the protons are what have the positive charge, and that nucleus is, quote, orbited by this cloud of electrons. So, thing is, a proton has a mass that is about 1,836 times the mass of the electron. So, because protons are so massive and because they are so tightly bound within the atomic nucleus, then objects that gain or lose positive charge are actually, what's actually happening is they are losing or gaining electrons. So when we say that it, quote, loses positive charge, what's actually happening most of the time is that it has gained electrons. Now, the exact details of that are not always completely true. For example, when you rub objects, sometimes you're rubbing off electrons or adding electrons to them, or sometimes if it's vigorous enough rubbing, you're able to break apart molecules and create molecular ions if they're not particularly well bound. But that here we're talking about more of a chemical process, so to speak, when I talk about, quote, vigorous rubbing in that case. Now, conductors. Conductors are a different sort of animal. In conductors, the charges are free to roam around. They're kind of, in the words of one of my old professors, Dr. Paul Wallace from Berry College at the time, the electrons are kind of like dogs off of their leashes. They're free to roam around the neighborhoods. And like if you have a cat, for example, that's going to attract all of the electrons. in that case, the cat would be kind of like a positive charge. So in the case of an insulator, on the other hand, it's like dogs that are stuck on their leashes, where the leashes are bound to the owners, in that case, the parent atoms and molecules. So in a conductor, you're talking about a sea of electrons. The dogs it's like the dogs are off their leashes. They're free to roam the neighborhood. So, a practical application of all of this. The third prong in an electrical outlet is the ground, and that generally connects a wire to something like a water pipe that travels deep into the actual ground of Earth. And since charges can move anywhere they want in a conductor, if there's a problem in your electrical circuit, for example, there's a short circuit somewhere, then that ground wire can drain excess charge without actually damaging the equipment or causing people to die or anything like that. That would be bad. So, as we mentioned, insulators are materials in which the electrons are bound to their parent atoms and molecules, so they can't roam around. However, even with insulators, you can have a bit of a polarization effect. The electron clouds around the atoms and molecules will shift if there is an electric field present. An electric field is something that is caused by charges. But that shift is not a whole lot, as we're going to see soon. And I'll also mention that this polarization happens not just with insulators, it also happens with conductors. It's just that with conductors, you're talking about a mass movement of electric charge, whereas with insulators, you're talking about individual electron clouds shifting back or forth. And how much of a shift is this? It's only about a femtometer, a femtometer being 10 to the minus 15 meters, 1/1000th of a picometer, or 1/1,000,000th of a nanometer. So the shift happens, so know your shift. It's just not much shift. So in the unpolarized situation, the atoms or molecules have kind of random orientations in terms of where the positives and negatives might be. Whereas if you apply an electric field, for example, you sprinkle a bunch of positive charges over here and or a bunch of negative charges down at the bottom, then the molecules will kind of move around in a line such that the electron clouds will shift more toward the positive end because it's positives that attract negatives and electrons are negatively charged. Now I should mention that this shift, this polarization shift, is actually something that can be measured. It can be tested. So we're actually going to do a similar type of calculation in a later example, but that will involve an actual mass movement of electrons. But it's the same type of principle. So you can approach an object of known mass with something that has a known charge and see how close you need to get in order to get that neutral object to move upward. And based on that mass, and thus the weight, you can estimate the number of electrons that are involved and assume that they all shift by the same amount. And then you can solve for that unknown amount. So that's how people can figure these things out. Now, how do objects get charged? We already mentioned charging by contact, where you take, say, a plastic rod or a glass rod and touch it to a metal sphere. That will transfer either electrons from the rod to the sphere or electrons from the sphere to the rod, depending on whether the rod is positively charged or has an extra positive charge or has a net negative charge. So, electroscopes are a device that help you to get a sense of how charged something is and how much charge has been transferred if such is the case. In this situation, we have a balloon, a blue balloon, that has been charged, and the balloon is brought near an electroscope. Now what this electroscope is, it's a situation where you have a metal ball and it's attached to a metal rod, and at the bottom of that metal rod you have two metal leaves that naturally hang together. And these metal leaves, they're on a very low friction hinge, and if charge ends up going down here into these metal leaves, then, well, that's like charge, they're going to repel each other. And this is a conductor, so the charges are free to move around. And it's suspended in this case, a glass tube by an insulating cork. So what happens if you simply touch it with, say, a plastic rod? Well, then you have transferred charge to this metal sphere, and that charge will get well, I shouldn't say evenly distributed, but get distributed in such a way that the whole thing has the same electric potential. That's a concept we'll talk about in a future unit. And as a result, these like charges will end up repelling each other. However, here's the weird thing. The same thing happens if you bring this balloon near it, but not touching it. What will happen is whatever charge the balloon has, that same amount of, remember this is a conductor, the same amount of like charge will flee away from the balloon, leaving the opposite charge near the balloon, and that like charge will end up causing the metal hinges in this electroscope to spread apart. And as you bring the balloon away, the metal hinges will get closer together. And the larger the separation, the larger the charge that has been either repelled down here or sent down here due to contact. In this case, a charge has been induced at the bottom, and we've really induced polarization because you have charge that's like the balloon at the bottom, charge that's opposite to the balloon at the top. But if you were just to charge it by contact, it would just be the same type of charge all around. So in the case with the rod, yeah, you're actually transferring charge. So in this case, this is simply charging by contact or charging by conduction, so to speak. Now, let me ask a conceptual question. If you have one of those electroscopes and you already give it a positive charge by touching it with a positive glass rod, and the electroscope leaves spread apart and the glass rod's removed, well, let's say you take a negatively charged plastic rod and bring it near, but not touching, the top of the electroscope. What will happen to the leaves? Will the leaves get close together? Will they spread apart? Will one leaf move higher and the other lower? Will the leaves not move at all? Will the leaves disappear? What will happen? So what will actually happen is the leaves will get closer together, because since you've already given the electroscope a positive charge, that positive charge kind of distributes all around the electroscope metal parts. And when you bring a negative rod nearby, some of those positive charges that are currently in the leaves, they're going to be kind of more preferentially attracted to that negative rod that is near the top of the ball, because at the top of the ball what you've done is you've repelled negative charges, so the negative charges end up kind of fleeing to the bottom, the positive ones end up coming to the top. What's really happening is simply the negatives flee to the bottom, canceling out some of the positive that's already there. Either way, you're dealing with less positive charge at the bottom, and the leaves are therefore going to get closer together because they're not repelled as much as they were before. So yeah, that negative rod creates an influence, and that attracts the positive charges in the electroscope. So this is a depiction of what's going on in a conductor when you bring a positive charge near what was originally a neutral metal sphere. The negative charges end up getting attracted toward the top, leaving behind positive charges at the bottom. Here, you are dealing with a polarization of charge. Now, you can use this principle to charge something by induction. In this case, give it a net charge without actually touching the object. So, what would happen if you had brought that simply a negative rod near in the neutral electroscope? Well, the leaves would be spread apart. The leaves would be spread apart. But if you brought the rod back away, then the leaves would come back together again. But what you can do is you can ground the electroscope while the negative rod is nearby. In other words, you can connect a metal wire to the electroscope such that when you bring the negative charges, and also connect that metal wire to the ground, of course, so the charge can drain out. So if you bring the negative charge near the electroscope, then what's going to happen is the negative charges are going to flee out from the electroscope through the ground wire into the actual ground. And then when you bring the rod away, then everything gets restored and the leaves get closer together again instead of far apart. But what if, while you have your charged rod near the electroscope, you take a giant pair of scissors and you snip the ground wire while the charged rod is near but not touching the electroscope? Well, Then, after these charges have flown out of the ground wire, out through the ground wire, well, they can't come back now because you've cut it. So you can bring your charged rod away, and since the charges can't come back, then the electroscope simply has a net charge. But it's a net positive charge. The rod that you brought was a negative rod. The like negative charges flew out of the ground wire. Flew out of the ground wire. And that meant that there was a positive charge on the electroscope. But then you snipped the ground wire, keeping the electroscope with a positive charge, and you now bring your negative rod away, but the negative charges can't come back, so you get a net positive charge. So whenever you charge something by induction, you're always charging it to the opposite charge as the item that you have brought nearby. So this is an important conceptual example to keep in mind. It shows up all the time on the multiple choice part of the AP exam. So there's your charging by induction diagram. Negative charges come near, and the positives get attracted to that side. The negatives end up getting repelled, but then you have the ground wire. The negatives end up going bye-bye, leaving the positives. You cut the ground wire, and what's left is just the positives. And that is charging by polarization. So, again, as I mentioned, make sure to understand that really well. Now, a good experiment is to do that with a Van de Graaff generator while a person is holding on. If the person then breaks the contact, but the person and the Van de Graaff bell are going to be charged, so to speak. And then you could potentially do this with, say, another Van de Graaff generator, and that other Van de Graaff generator would end up getting an induced opposite charge if you had the ground wire connected. So anyway, if you missed some of that, then make sure to go back and replay the video. Now, what about charging a neutral object with a neutral object? Well, guess what? This is how static electricity works. Certain materials like to collect electrons, whereas other materials like to give them away. We've already talked about that with glass rods and plastic rods. This is called the triboelectric effect, where you have two objects, different objects, that after being rubbed together can transfer charge to each other, acquiring a charge, or if they're already charged, they would have a larger charge difference than before. So this is the triboelectric effect, long story short, is charged by rubbing. This is how bumblebees can transfer pollen from flower to flower. So as they fly through the air rubs against them, giving them a little bit of a net charge, and then the pollen molecules end up sticking to them. They originally are neutral, they end up getting polarized and thus attracted to the bumblebees, just like you comb your hair with a plastic comb, it can pick up bits of paper, same idea. And then the bumblebee flies off to other flowers and distributes that pollen all around, and you get flowers all around the world. Some materials do this more so than others. This is the triboelectric series. For example, this is simply a conceptual depiction, so don't take these numbers literally. But human hair loves to give away electrons. So if you comb with a rubber comb, the rubber likes to take those electrons, your hair likes to give them away. So after that, you can stick a neutral balloon on your hair and it will stay there for a time. Or you can rub a rubber balloon against your hair. Same type of thing will happen. The balloon will be charged, and then you can magically stick it against a wall, and it'll stay there, especially if it's during the winter time. So, long story short, the farther apart two materials are on the scale, the larger the charge difference that will be created when you rub them against each other. So, let's say you rub human hair with a balloon. Which object would become negatively charged? Well, assuming that this is a rubber balloon, because rubber likes electrons somewhat. Human hair loves to give away electrons. It hates electrons. So the rubber is going to become negatively charged because it likes the electrons more than the human hair. What about nylon on human hair? Oh, both of these hate electrons. They like to get rid of the electrons. So will both of them just become negatively charged? which object will become negatively charged, if any? Well, it'll actually be the nylon. In other words, this isn't saying that this will always become positively charged. It's just saying that this will preferentially become positively charged when rubbed against typical, say, neutral materials. But if it's rubbed against a material that wants to become even more positively charged, then yeah, the nylon's going to become negatively charged. So that's something to keep in mind in this triboelectric series type of situation. So here is a table with actual numbers for a variety of substances. And with the actual numbers, we can see how we would be able to make calculations and compare things. Whereas with the previous table, it showed it in a more visually appealing format. So which would give you greater charge, at least larger charge, a larger amount of charge? Would it be, say, paper rubbed against vinyl, or would it be box sealing tape rubbed against PVC? Well, paper rubbed against vinyl, well, that's a difference of 85 on the scale. So paper, so 10 nanocoulombs per joule minus negative 75, that's a difference of 85 nanocoulombs per joule. Whereas box sealing tape rubbed against PVC would have 55 minus negative 100, and that would be 155. So that is a noticeably larger difference. So the result would be that you would have a larger amount of charge getting transferred when you rub box sealing tape against PVC compared with just rubbing paper against vinyl. Now, what to know about triboelectricity? Well, you need to understand the general idea of the series and how the effect works, and understand that you also won't actually need to perform any calculations with this. It's more of a concept. So now that we've talked about the triboelectric effect, let's discuss a very spectacular version of static electricity, that is lightning. So in Ben Franklin's famous kite experiment, long story short, his kite was not actually struck by lightning. What actually happened was that lightning struck nearby, and by doing so, that ended up transferring charge to the metal key, and it was glowing. The fact that it glowed, this is what we call coronal discharge, and this glow showed that, yeah, it actually was electrically charged. Franklin himself was indoors, but because of the fact that there was a large potential difference between where the lightning struck and where he was standing, and that he was potentially connected by that kite string between a place near where the lightning struck and where Ben Franklin was, he could have died, especially if the lightning actually had struck closer to or on the kite. So here is a nice picture of coronal discharge of metal keys as they are being charged by a Tesla coil. St. Elmo's fire is an example of coronal discharge, and sailors actually saw it as a good omen. But actually it's a sign of great danger because the ship might be about to be struck by lightning. So I guess the sailors who survived saw it as a good omen. Another version of this, where you have an airplane flying through the sky. In fact, there are videos of this phenomenon where in a particularly charged atmosphere, especially around thunderstorms, the plane flying through, well, that air rubbing against the airplane wing, you can have a transfer of charge there, and once enough charge builds up, it ends up eventually creating a large enough electric field that it's able to ionize air molecules and get discharged through the air. In fact, that's actually how lightning itself occurs, just on lightning occurring on a much larger scale. Ben Franklin also performed a famous bell experiment. Here's the idea with the bells. When you set up two bells with a metal ball in between, and one of the bells has a wire going up to a charge source, like say the roof, where, in other words, it's closer to where the electric field source is originating, i.e. the bottom of a thundercloud, and then you have another wire going to the ground. So what can end up happening is as a thundercloud goes overhead, that can transfer charge particularly with the bell with the wire that's connected to the roof, and if there's any charge transferred to the opposite bell, it's going to be the opposite charge. It's going to be the opposite charge. So that is going to induce polarization on the metal ball that's in between, and that metal ball is going to go to one of the bells. It's going to go to one of the bells. Whichever bell has the larger amount of charge. It's going to, let's pretend it's the one on the left, it's going to touch that bell on the left. Some of that bell's charge gets transferred to the hanging metal ball. Now they have the same sign of charge, so they repel, but now this metal ball has opposite charge as the bell here, or maybe it's neutral, but it ends up getting repelled from the bell on the left, and as it approaches the bell on the right, that either gets attracted because of the fact that they are oppositely charged, or it gets attracted because of the fact that it's chasing away the like charge down the ground and attracting the opposite charge, which ends up, since the opposite charge is closer, remember closer charges end up giving stronger forces, that is going to cause the hanging metal ball to touch the right bell. But that will either transfer its charge and become neutral again, so nothing will happen, or they will now end up sharing the same charge, repelling each other again, and then the cycle continues, and the ball just goes ding, 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 and that was one of Ben Franklin's experiments to show that there is a thundercloud overhead, in case he couldn't actually look out the window and see it. In the case of actual thunderstorms, so here we're just going through general information. This isn't going to be on the AP exam, but just general bits of knowledge to know. Most of the time, about 3/4 of the time, what's happening is around the bottom of the cloud, you have negative charges accumulating. You have negative charges accumulating. This charge separation happens due to, quote, rubbing of air masses. Thunderstorms are very energetic areas. You have lots of convection cells throughout the thunderstorm, and so you'll have some air going up while other air goes down, and the air that's going up versus the air going down will have different amounts of water vapor, different temperatures, and stuff like that, so they will have different triboelectric preferences, so to speak, and that will end up resulting in charge separation. This is the way we currently understand it. We actually don't, as far as I know, completely understand 100% exactly how the charge separation occurs. But in any case, you end up getting negative charge accumulating at the bottom of the cloud, the positive charges at the top. If you have in-cloud lightning, this will become so large that it ionizes air molecules, and air molecules that are ionized, well, what does ionization mean? It means that either electrons have been kicked off, or it means they have extra electrons. Usually it means that electrons have been kicked off because the energy is so high. That's called a plasma, by the way. And once that happens, well, this charge is attracted to go in there, and it ends up creating an arc up to that top, and you end up getting a massive charge transfer. But the same thing can also happen on the ground. When you have this big amount of negative charge at the bottom of the cloud, it ends up chasing away the like negative charges from the ground, inducing positive charges underneath the thundercloud. And this will create a strong electric field. And once the electric field becomes strong enough, again, the air becomes ionized. We call this dielectric breakdown. And once this dielectric breakdown occurs, you end up getting negative charges starting to stream off from the bottom of the cloud to eventually connect to the ground. And once that occurs, once the connection itself occurs, that is when you have a channel. And then when that channel is made, the charges stream through there at very high speed, heating up the air really, really hot, really, really quickly. And that starts actually from the ground up, is where you actually see the flash. So the charge goes from the cloud to the ground, but the flash itself will end up going from the ground to the cloud. And if you look at lightning in slow motion, that actually is what usually occurs. Now, I mentioned that happens about 75% of the time. The other quarter of the time, it's actually positives on the bottom and negatives at the top. and the same thing happens. And in that case, we have the flash actually going from the cloud directly to the ground. But the streamers will appear in the opposite direction. Because remember, it's negative charges that move. Since the electrons are much lighter than protons and ionized atoms, that means that, well, remember, force equals mass times acceleration. The same amount of force is there, but the much less massive object will be the one that gets accelerated much more quickly. So yes, in the typical situation of what we call cloud-to-ground lightning, the bolts themselves actually travel from the ground up, but that occurs after the charges have met and created the channel. In other words, the flash occurs just after the electrocution has already occurred. So if you think that you have such incredibly quick reflexes that you can dodge a lightning strike, well, here's the problem. You don't see the flash until the charge transfer has actually occurred already. So, in other words, you've already been electrocuted by the time you see the flash. And that's not even taking into account the fact that, well, the flash itself occurs at the speed of light. The charges themselves actually get transferred slower than the speed of light, thankfully, because there actually is something you can do. But you're not going to be able to dodge the strike itself based upon first seeing the flash, because when you first see the flash, the electrical strike has already occurred. Now, because of the fact that this does create a very large electric field, it means that if you are in the middle of a large field, you might actually, a large grass field, I mean, where a large electric field is starting to occur because of a thunderstorm, your skin will start to feel all prickly because the hairs on your skin will be standing up. It's because you actually are starting to be charged at that point. And at that point you realize, okay, you might be about to get struck by lightning. So what you can do is, well, if it's a small field and you're really close to a building, then you can run inside of the building. I know somebody who did do this and got saved. He recognized what was happening. He kind of felt all prickly on his skin. He ran inside, and 20 seconds later, lightning struck that spot where he had been standing. But if you're in the middle of a large field, you might not necessarily have this option. So the recommendation in that case is to squat down with your feet close together to decrease the path length difference between your legs as much as possible. The reason for that we're going to talk about very soon. And by squatting down, that decreases the chances that you're going to suffer a direct strike because of being the tallest thing around. And with your legs as close together as possible, if there is a strike nearby, that decreases the amount of electricity that will actually flow through you. Now, about this path length difference, the reason this is important is because electricity occurs when you have a source, a voltage, so to speak, an electric potential difference between two different objects. When you have an electric potential difference between two different objects, electricity is going to flow between them. And how much current's going to flow depends on the resistance, the electrical resistance between those objects. In the case of a lightning strike, there's originally a large amount of resistance between the bottom of the cloud and the ground, but as the electric field gets larger and larger, once it starts to ionize the air, suddenly that electrical resistance goes down to almost zero, and then you have this massive flow of charge. But in any case, it's the electric potential difference, i.e. the voltage, that determines how much electrical current is going to flow between point A and B. Well, actually, it's the voltage combined with the resistance between them. That's Ohm's law. We'll talk about that in a future unit. In any case, the larger the potential difference, the larger the amount of current is going to flow. Well, in the case of a lightning strike, a lightning bolt has something like 100 million volts in terms of its, quote, electric potential. But a point far away will have zero. So what really matters in terms of figuring out how much electrical current is going to flow through your body is what is the electrical potential difference between your two legs. If you are standing with your legs spread apart, then your leg that is closer to the lightning bolt will have a larger electric potential than your leg that is farther away from the lightning bolt. Well, that means that there will be a potential difference between your two legs, and therefore electrical current will flow through your body. And of course, the closer you are to the lightning strike, chances are the larger that electrical potential difference will be between your two legs. The farther you are away, the smaller it's going to be. In other words, like 0 compared with 10, as opposed to a million compared with 1.1 million. Yeah, that would be bad. And my units there were volts. But in any case, let's take a look at a tragic situation, a couple of tragic situations. So in class I show some lightning strike videos, and in one case lightning strikes a tree, and you notice that the entire tree itself lights up. So yeah, it's bad to stand under a tree during a thunderstorm. And in this case, we have some cows that all bit the dust because I guess they kind of felt something was going on. They might have felt kind of prickly, so they all ended up standing together near a fence during a thunderstorm. Lightning struck nearby, but since they were standing together, pretty much huddled together, that meant that there was a large electric potential difference between the first cow in the herd and the last cow in the herd. And they were standing together, so you had that large electric potential difference. So there ended up being a large amount of current going through the cows, and they all ended up dying. So another bad situation with this was back in 1939, where over 800 sheep were killed when they all gathered around a tree that got struck by lightning, and that discharge spread out and went through the entire herd. And each animal was touching another animal, so there was basically a continuous route through which the current was able to travel. So here is a link to a televised soccer match where lightning strikes probably somewhere on the field or nearby, and several of the players go down. But not all of the players go down, and there seems to be relatively little relationship between where the players are standing and who goes down. In other words, it's not like, oh, all the players on the left side of the screen go down. No, it's players who are scattered about. So the ones who went down were the ones who, at the particular moment when the electrical contact was made, just before the actual flash, the ones who happened to have both feet planted on the ground, and such that the feet were kind of parallel to a line going from the player to where the strike occurred. Because if it's parallel to that line, that means one foot is noticeably closer to the strike than the other foot. But if they were perpendicular to that, then each foot is roughly the same distance from the strike, so there's not much potential difference between the feet, and they were fine. And players who happened to be running at the time and only had 1 foot or 0 feet on the ground were also fine. So that's how that can occur. So yeah, you're safer if the distance between your feet is small, or if the line connecting your feet is perpendicular to the line between you and the strike. So that's something to keep in mind. I also want to mention that when you are in a metal car, you are safe inside of the metal car because you are sitting in what we call a Faraday cage. One of the rules that we're going to get to later in the course is that inside of a conductor, you are not going to have an electrical field. That you're not going to have an electrical field inside of a conductor, because that if you did have an electric field inside the conductor, then that electric field would end up chasing the charges around the conductor such that they would end up distributing in a way until the electric field is gone. Otherwise, they would keep moving. So inside of a conductor, at least one that's in what we call electrostatic equilibrium, you're not going to have an electric field. So basically, you're safe in a metal car that gets struck by lightning because of the fact that the charges end up distributing themselves in a way such that electrical fields inside of the car end up getting canceled out. It has, I should mention, absolutely nothing to do with the fact that the car has rubber tires. Because if you think about it, if the lightning can make it all the way from the bottom of that cloud that's thousands of feet up to the ground, or at least to the car, then surely it can make it another few feet from the car to the ground. So whether the car's tires were rubber, gold, iron or whatever, it wouldn't matter. You would still be safe inside of the car if it has a metal frame. However, if you have one of those cars that has a frame of carbon composite, that would be bad. You'd be dead. So just something to keep in mind in a car during a thunderstorm. Of course, if you're inside of a carbon car, then there's also a lower chance that it gets directly struck to begin with, but it's something to keep in mind. Also, when there's a thunderstorm around, it would be unwise to take a bath or a shower because of the fact that lightning can travel through the water and also through your pipes, your metal pipes. So that's something else to keep in mind. Next, a few more fun things about lightning. You can get lightning in volcanoes, or at least in volcanic eruptions. So this is the famous eruption of the Icelandic volcano Eyjafjallajökull that occurred back in April of 2010. This was the one that caused all kinds of travel disruptions throughout Europe. They had to shut down air travel in Europe for, I think, a week or so because the little tiny particles, the silica dust from the volcano, if it got ingested by the jets in jet aircraft, then that could melt and get coated on the engines themselves, and that would end up being real bad. The engines would die off, and you kind of need engines to fly a plane. Now, here you have different amounts of dust, different compositions and everything rubbing against each other that ends up creating a lot of static electricity, and you get some nice lightning strikes. Here is another picture from, I believe, that same volcano, just a slightly clearer shot, and then a farther away picture of Chile's Calbuco volcano that erupted in April of 2015. Now, you can also have lightning on other planets. An early example of this was originally possible detection of it in the atmosphere of Venus by early spacecraft, I think even going back to the 1970s, but they weren't so sure. But then when the Venus Express mission went to Venus, they were pretty sure that they detected a very strong surge in electric field at some point, and that kind of confirmed that you do have lightning occurring in the atmosphere of Venus. You also have it in Jupiter and Saturn. So here's a picture of Saturn. I should mention that lightning strikes in storms, even in the atmosphere of Jupiter, are about 3 times more powerful than they are on Earth. But in Saturn, they can be like 1,000,000 times more powerful because Saturn's atmosphere has less water vapor, and so with less water vapor, that means that more and more charge can accumulate before it ends up discharging through the static electricity of lightning. Now, speaking of static electricity, you can produce lightning yourselves. Every time you end up zapping a wall when it gets cold and dry during the winter, that is static electricity, and that's basically just a small form of lightning. A typical static discharge, depending on how strong it is between about 20,000 and 40,000 volts. And it's actually quite a large amount of current. It's about 2 amps of current, which would be enough to kill a person easily if that amount of current was sustained. In fact, even just a fraction of an amp is enough to kill a person. But luckily it only happens for less than a microsecond, so there isn't all that much energy transferred, so it's not enough to do any damage. But yeah, these types of static strikes, the same thing happens with lightning, just on a much bigger scale. And picture of Saturn, there's another nice dragon storm with Saturn, as they called it. These are infrared pictures, I should mention. Now, we already mentioned that you are safe inside of a car during a thunderstorm, at least a metal car, and it has nothing to do with the rubber tires. And that happens because the electric field is 0 everywhere inside of a conductor. And if that wasn't true, then the charge would end up moving around. And generally, we call such a situation a Faraday cage. And any excess charge in a conductor will be on the surface because, after all, it's a conductor. Charge is able to move around as much as it wants, as long as it doesn't exceed the speed of light, at least. And that means that any excess charge is going to be on the surface. And that occurs, it turns out, because there is a 1/distance squared dependence on the electrical force between charges, which we're going to talk about soon, but it turns out that if you had some other dependence on that force, you would actually get some accumulation of charge in the center. And a proof of that, at least a proof of the fact that this ends up working out, is a Gauss's law problem, which is going to be in the next unit. So we talk about electrostatic equilibrium, in other words, that everything has kind of come to a certain charge distribution that is not changing quickly. When you have that, if you have a conductor, at least, and it's a conductor with an irregular shape, a result of this is that charge tends to accumulate at the pointy ends. Now, a popular misconception of this is that this is why lightning rods have pointy ends, that if they have these types of pointy ends, then that will allow a very large electric field to occur at those pointy ends, and that will discharge any excess charge that builds up on, say, a house that is attached to a lightning rod. The idea is that this charge would end up going to the lightning rod, and then it would discharge out the pointy ends, because that would end up ionizing the air, and it would drain out that way. The problem is, this happens way too slowly in the case of a thunderstorm. Now, you simply have the pointy ends to help to kind of attract the lightning a little bit and redirect it into the ground wire as opposed to throughout the house. In fact, in a lot of places, for example, in Europe, and I believe I've seen it in China, the lightning rods will be bell-shaped at the end, so that that you can also produce a large electric field that way to help to attract the lightning to that spot. So something to keep in mind, because there is that popular misconception that's like, yeah, you need those pointy ends on lightning rods in order to discharge the electricity from the house. I've seen this misconception in a number of physics textbooks, so it's something to keep in mind. But yeah, the discharge happens way too slowly compared with the rate at which the charge is building up when there's a thunderstorm nearby. So here is a nice example of a Faraday cage being zapped with probably millions of volts of electricity. Also, if you go to YouTube and Google Arc Attack America's Got Talent, you'll see some videos where this group called Arc Attack some years ago performed, quote, songs that were being, quote, sung by a singing Tesla coil, and that was charged up to millions of volts, and the performers wore metal suits so that when they got zapped, the electric field inside would be zero, and any excess charge would just be distributed in such a way around the metal suits such that that was the case. So next, we will talk about Coulomb's law. How do electric charges interact with each other? Numerically, not just conceptually, but numerically, how do electric charges interact with each other? We're going to talk about that in the next video. So until then, thank you all for watching, and have a good one.